I believe we can start, right? Or do we want to give people a few minutes to join?
I guess start the introduction.
We can start. Awesome. Well, hello everyone. Thank you for the time to register and to join us today, and also for being part of the Analytics and Big Data Society. My name is Boyana, and I work at Centelli Solutions, which is data science consulting firm, and I also manage marketing and events for the Analytics and Big Data Society. I will give you a quick background on the society. For those who are joining us for the first time, the Analytics and Big Data Society is a nonprofit organization based in Charlotte, North Carolina, which believes in the use of data for social good. The mission of the society is to establish Charlotte as a national analytics and big data hub. Throughout the years, we've been carrying this message through the various events we've been hosting, such as these monthly analytics, data analytics speaker series events in partnership with the UNCC School of Data Science. Thank you, UNCC. The ABD Society also hosts signature series events each quarter, which are on a larger scale, happening in person 3 times a year. And lastly, our biggest annual event, the Queen City Hackathon, this year was hosted in Red Ventures in February. We got lucky there. Our upcoming event is December 3rd, so continue to follow us on social media platforms and don't forget to register. I will be moving on to our speaker for today. And I would like to welcome NIKOLAOS VASILOGLOU. He is VP of Data Science at Relational AI based in Georgia. Dr. VASILOGLOU holds a PhD from the Department of Electrical and Computer Engineering at the Georgia Institute of Technology. His thesis was focused on scalable machine learning over massive datasets. After graduating from Georgia Tech, he founded Analytics 1305 LLC and Ismion Inc. He has architectured and developed the Paperboat machine learning library, which has been successfully integrated and used in the Logic Blocks and HPCC systems platforms. In the past, he organized and chaired MLConf and Executive Machine Learning, a series of conferences in machine learning held in New York, San Francisco, Seattle, and Atlanta. And in his spare time, he continues to offer training in the US through ML Train and the Machine Learning by Example meetup. To integrate machine learning concept in practice, Dr. VASILOGLOU has served as a machine learning consultant to PredictX, Revolution Analytics, Damballa, TapeD, and LexisNexis, and he helps local Atlanta startups with machine learning systems. Well, that was a long background. And today he will walk us through the embedding 500-year-old idea that married deep learning and dominated the world. Before I hand it over to NIKOLAOS, I would ask you to do not hesitate to submit your questions at any time. Nick will address them in the meantime. Nick, now I'm handing over to you.
Thank you very much, Boyana. Hi, as you heard, I'm based in Atlanta, and we are maybe an hour before we announce the result here in Atlanta, the election. So during this hour, we're going to take a journey and talk a little bit about an interesting idea, a fundamental component of AI, that is a really, really old idea, but it's the fundamental block. It's what fuels and powers most of AI applications. So our journey will start in Greece about 2,500 years ago, And this is the day where, you know, the days of Euclid. That was when Euclid was doing geometry. In reality, people don't realize, but the Elements of Euclid was a book that was mostly about logic. Okay, he kind of saw geometry as a logical theory. So as you can see over here, for A was a point. It was an entity that, you know, characterized as a point, and an edge on a triangle is a relationship between point A and point B. And any theory, if you want, you know, you can always write it into this form. You can say that basically for every triangle, the sum of angles is 180. You can write it as a logical expression. That's what this is formal logic, for those of you who know. So Euclid really kind of like established this idea of logic and geometry and theorem and proof theorems. His biggest problem was that he could express relationships, but when it comes to measurements, so when I need to go and measure, you know, this angle or the length, I have to assign it to a number. So, you know, you start with concepts, point relations, like edges, and then you get this idea of a number. So how does this number fit over there? And you know, if everything is symbolic, what is x? Like, what people don't realize that in geometry, x can only be one. You know, when you construct something, you know, the theorems of Euclidean geometry, they tell you how to construct a square, how you can construct a circle, and if you really want to construct an angle, the only angle that Euclidean geometry, the basic theorems are giving you is the right angle, because, you know, you talk about the parallel lines and the line that connects two parallels. This is the 90-degree angle. So you know, so you can do a lot of stuff with that. By just with these symbols and the notion of repetition, you can construct, like if you want to construct the square root of 2, you take an isosceles orthogonal triangle and boom, the hypotenuse is square root of 2. If you, here's kind of like some constructions about how you construct the square root of 5. If you want to construct the rationals, you can also do that. But these are kind of like some ways that in, like if you want to construct the 1/2, this is how you do it, you know, you draw this line. Euclidean geometry gives you a lot of tools to compute every number you want, almost every number. And you know, it took several centuries, and people realized that work hard, and they discovered the real numbers. And this is the 2 great books. By the way, I'm going to be mentioning a lot of books during this presentation that you know, if you get inspired, you can read more. And it took several years to discover the real numbers, and a lot of logicians and mathematicians worked to prove that they actually exist. Okay, and if you really want to follow this this line of thread, you know, philosophers are still arguing whether the real numbers exist or not. This is a great book to talk about. Now, what is great about reals is that reals can really represent outputs of complicated programs and concepts or any sequences really well. So, you know, for example, in Euclidean geometry, you had to create a shape in order to compute the 1/3. You know, right now you can just represent this whole construction with the number 0.33. Like, and the square root of 2, you don't really need to carry with you an isosceles or triangle, right angle triangle. You can write it as numbers, and you know, anything complicated you want, you can write it like you know, in terms of numbers. So the nice thing is that all this nice complicated geometry can be standardized with just a sequence of numbers. And this is really great because we can compute distances between these numbers very easily. You know, subtractions basically computes the distance between two numbers. up to some approximation error. Okay, and we can do these computations like, you know, in Euclidean geometry, if you had to compare two line segments, you have to compute a complete proof to show which one is bigger than the other or smaller. Now, the cost that you're paying is that all these computations now become approximate because, you know, if you really want to, not all real numbers can be represented with a finite number of digits. Pi, for example, cannot be, that's an example, cannot be represented with a finite number of digits. So the reals, you can think about them as taking, you know, concepts, logic, and everything, and arithmetizing them. And that's a great thing. And thanks to Turing, Alan Turing, I highly recommend getting inspired by him and reading his book, or even watching the movies like The Imitation Game. He's the father of computer science. He basically said that you know, almost you can represent almost everything with reals. It's just not easy always to compute them. And this is a book that talks about a number that we can define it, but we cannot compute it. Anyway, what you really need to keep from this introduction, this 2,500 year trip, almost 2.5, we haven't really reached, we're about in the 1800s right now, is that the real numbers, they call, you know, they perform an operation that is called embedding. They take, you know, complicated shapes, programs, sequences, concepts, and they map them into a number. Okay, so this was great, but now we are, you know, I think 1800s in France, during the Enlightenment period. This is our next stop, where someone, a very famous philosopher and mathematician, René Descartes, he also had a brilliant idea, an idea that changed the way we think. He invented what we call the analytical geometry. He said, well, these triangles and shapes that Euclid was playing with, I can actually represent them with a tuple of numbers. Now that I have real numbers, I can represent every point now with two numbers. And this is great. So if I have a triangle, you know, before I was saying that A is a point, B is a point, C is a point, and the edge is A comma C. Now I can give you these three tuples of numbers, three pairs of numbers, and I'm telling you a lot of things that you can do. Now, the key point in Cartesian geometry is that geometrical shapes are connections of, it's a collection of vectors. Vectors consist of real numbers, and dimensions are pretty much independent. Like, it means that they are orthogonal. Okay, that has an implication. It means that you live in a flat world. We might have the opportunity to talk about that later on. This presentation, I warn you, is a really long presentation, like a 2-hour presentation. I'm going to give you half of it today. So Cartesian geometry is brilliant. In other ways, we also call it analytical geometry. Is because if I want to compute distances or angles in Euclidean geometry, I have to construct a program. I have to construct a proof, an algorithm. In Cartesian, distances and computations and angle computations are fairly easy. The proofs, anything you can prove about triangles or geometrical shapes, requires you know, something called A-star sets and other complicated methods. Here we can just use calculums and theorems from reals. Okay, so if you want to prove the Pythagorean theorem in analytical geometry, it's pretty easy, pretty trivial. So basically, you know, we went from logic to Cartesian and real numbers. That process, we call it embedding, and we had to go through you know, through this process. But there was like one part that was missing, you know, like why did it take 2,000 years to almost 2,000, more than 2,000 years to go from Euclid elements to more to analytic geometry? It's because we needed these two guys. Like Descartes wouldn't have been able to do it without the help of this guy is Newton, and I think this guy is Leibniz. They both claimed that they invented calculus, and they were hating each other. They had a feud. So we needed these guys. These were instrumental. We're not going to talk about them too much, but they are the ones that map like shapes to integers. Now, to numbers. Now, I want to give you an example just to understand in mathematics or something that is close to data science over here. We're going to see it in data science soon. You know, if someone was giving you 4 points, okay, one way of describing them is by giving you, you know, their coordinates. You know, this is at 0, 0, 1. This is 0, -1. This is 1, 0, and this is -1, 0. Okay. But there is a different way that he can give you. He can give you the distance between blue and yellow, the distance between blue and green, the distance between blue and red. So in other ways, all pair distances. So this, we call this the relational representation, because I'm not giving you the Cartesian coordinates, but I'm giving you the relationships between all pairs, okay? And this has a storage requirement, which is n times 2 or n times d if you're in higher dimension, and this is n times n. Okay, so that was a result. That was an example in data science, in mathematics and geometry. I want to give you an example in data science right now. So, you know, if you've ever done any work in machine learning, if you are a data scientist, at some point in your life, you must have seen the iris dataset. Okay, this is one of the oldest datasets in machine learning and in data science. Has about 157 points, and what it does, they took flowers. It was a botanist, a biologist, and I can't remember who did it, and he was trying to classify 3 different flowers, and he was measuring, you know, for every flower he was measuring the sepal length, the sepal width, the petal length, and the petal width. Okay, and these were your features, and you had to classify them in 3 different classifications. So this is a nice Cartesian data set, okay, because you have numbers. Now, that was probably the last time you saw a Cartesian data set, because you know, once you finish your data science degree and you started working on real problems, you realize that everything you work with in real life is a relational data set. Whether this is a graph that you see on the top left, or on the right, text is also relational because you have words that one follows the other. So it's one relation, but that's pretty much it's sufficient to build these long chains. The same thing in biology if you were working with DNA. Images are also relational because you have pixels that they are related to their neighbors. And of course, in the down here, you see the tabular data that they're coming from enterprise databases. This is a classic example of databases with movies and directors and actors. So they're all like relations, okay? So relations are everywhere. And here I'm giving more examples. You know, when you need to work in data science, most of the tools don't understand relational information. They somehow need to convert it to Cartesian, okay? And life was great with hot encoding. The very first time that bag of words was actually used wasn't really in text. It was used in images, and it was used in the JPEG compression back in the 80s. I don't have time to talk more about it. But if you're familiar, or if you're not familiar, whenever you have you know, some simple relational data, you can encode them with a bag of words representation. Now, Word2Vec kind of like made this relational, you know, because here you're missing the order, okay? But that was okay in the beginning. Word2Vec was probably the first algorithm that kind of like drew the attention. It's not that we didn't know it, but we need someone to do that. So you know, here you see an example where it's text, and you see that it's a simple graph, it's a chain. And the relation, with relation and a little bit of logic, which the relation is that two words are connected through the next to predicate, okay, that next to founder is SDSC. And the logic is that if A is next to B and B is next to C, then C must be also close or next to A. You know, maybe we should talk about that. Sorry, just a second. So here, what I'm saying is that you would have been able to implement that with a SQL database. Okay, so you can put all your relations, like you can take your text, put it on a database, and then this query basically computes the co-occurrence matrix. This compute the co-occurrence between words that are 2 hops away, 3 hops away, and that is sufficient to give you words that they are related by just like finding how many hops they can be, far away they can be. You know, modern graph databases can do this much better than SQL. These are 2 of my colleagues that they have pioneered this research. But geometry, the truth is that can do this kind of reasoning much faster. Okay, so if you use word2vec, you know, you will realize that words that they you know, you don't necessarily have to use deep learning, but you will realize that the words that they tend to co-occur, they're going to be placed closer, and words that they don't really co-occur, they're going to be far away. So embedding really, you know, solves this problem for you. Instead of writing this nasty program over here, you can run a deep learning algorithm and you know, and get this kind of picture. I'm pretty sure you've seen this example of word2vec with capitals and all these sorts of other things where they show how close things can be based on how they appear in a document. You know, there are other types. There's lots of embeddings where, you know, they can compute the shortest path by just computing a distance, and you don't really have to run some nasty optimizations. Also, you can have relations with ordering, where you can have a relation love, where you can say Moham loves team more than Nick loves Amir. So you can have even relationships that they can hard to quantify. You can create an optimization problem. And I'll show you an example, okay? And here's what I'm trying to say. This would make, if you haven't understood anything so far about the embeddings, this example, it's gonna make everything clear. So you see all these points over here, and I'm pretty sure, I don't know if people can talk. Let's see, well, we have participants over here, but what you see over here is probably is cities from the US map. Okay, so this is the US map. Now, what is interesting is how this map was constructed. Okay, what we did is we took pairs of cities, actually triplets of cities, and we said, you know, I don't know this distance between San Francisco and Los Angeles. I don't know the distance between San Francisco and New York, but I do know that the distance between San Francisco and New York is larger than the distance from San Francisco to Los Angeles. So imagine that you're taking triplets like that. You know, Chicago is closer to Atlanta than it is to San Diego. So you can pick as many triplets as you want. You feed them, so these are your relations, okay? You feed them in it doesn't have to be deep learning, in an embedding method, and it assigns, you know, 2 numbers, and then you plot these numbers, boom, you got, you know, the cities placed in the right place, so you can reconstruct the matrix, the map. Okay, so here's a question. If embeddings can do reasoning, are they better than symbolic reasoning? Okay. So you remember when I talked about the real numbers and how beautiful they were, I said that you can compute distances between points by just subtracting on the line the two numbers. I could take two numbers, subtract them, kaboom, I have the distance. Now when you're having higher dimensions, the distances or dot products can compute something more complicated. For example, I mentioned before that a distance can, in a Euclidean domain, you can, on the two dimensions, can compute the shortest path, or they can compute the semantic similarity between two words, or they can compute, whether two people are brothers or not. Based on how I have constructed the embeddings, the distance can have a meaning that has to do with a specific relation or the dot product. But keep in mind, they are approximate, okay? They compute these relations or this reasoning, and they need a lot of offline computation. So this, in order to get into this two-dimensional map, I probably have to spend hours training my models. Now, there's also something else. Symbolic reasoning can be slower, as I showed you with this SQL example, but it's not static, okay? Which means that if I give you some relations and some rules, and I ask you to find out who is the grandfather, who is friend with whom, who loves whom, yes, you have to do some symbolic computations, and you can find them, and it might take some time. But then if I come and change the rules and I say, oh, in order to be friends with someone, you need to know him at least 5 years and live in the same city, and I change the rule, then you can repeat the symbolic computation on the fly. Now, that's not the case with embeddings, because with embeddings, you have to give me the rules and the relations ahead of time. I have to train my deep learning model, and then I can do inference. If you come back and you change one of the rules, I have to go and retrain it. So one way of thinking it is between compiler vs interpreter languages, okay? So when you're working in C++, for example, you write a program, then you have to compile it with a compiler, which takes time, and then you can run it. Now, if you want to change the program, you have to recompile it. Versus when you're using Python, Python is an interpreter language, which means that it's slower because, the compiler, it sees the whole program ahead of time. It can do a lot of optimization. In Python, when you write a program, it just interprets it on the fly. It just executes one command after the other. But the nice thing is that if I change a few Python commands, I can rerun it and it will be pretty fast because it doesn't really have to recompile it, okay? And in the end, I want to say that embeddings have the same reasoning power with symbolic systems. We don't have any evidence that embeddings and symbolic systems are have an advantage one versus the other. It's just a different way of doing the reasoning. And if you are interested, there's this nice book from 2015, I believe, 14. The Master Algorithm by Pedro Domingos, where he talks about the 5 tribes of AI, and there are the symbolists and there are the connectionists. The symbolists are use symbolic reasonings. The connectionists are using deep learning and embeddings. Okay, now the next question that we have to address is, why do we want to convert relational data to Cartesian? Okay, I showed you before that there is a way. We didn't really dive into the algorithms, but we saw this simple example with these 4 points where I showed you the Cartesian and the relational. And you see that I have some corrections done by someone called Joshua Bengio. So Joshua Bengio is one of the 3 Turing Award laureates that for deep learning. Turing Award is something like a Nobel for computer science, and Joshua Bengio is one of the 3 fathers of deep learning. So he doesn't like the word relational. Instead, he used the word local. He doesn't like the word representation, data. He prefers to call it representation. and he doesn't like the word Cartesian. He's using the word distributed. Okay. If you follow Bengio's research, you will see that he started publishing, and I happened to be a PhD student that time, and actually in the same area. You see the word manifold, 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 manifold again and again, and all of a sudden, in 2008, which coincidentally was 2009 actually, the year that I graduated, he started talking about deep learning instead of manifolds anymore. Quite sad, because I missed the wave just in just in the razor thing, so I kept doing my research, obviously, and I was following his research, but it would have been nice if I had been in that wave. So we're going to talk about manifold, and by the way, these ideas are the same, exactly the same ideas that they are behind general relativity. If you ever watch the movie Interstellar, which I highly recommend, it's based on things that we're going to discuss right now. So you heard several times that when you're on a flat surface and you want to find the shortest distance, you just draw a line. But I'm pretty sure you've seen the aeroplane routes on Earth. They don't follow straight lines. They follow the lines of the shortest path, and these lines are circles. So we call these the geodesics, because if you want to go from New York to London or to South Africa, you don't draw a line. You're not going to drill through the Earth. You have to follow the curvature of Earth. Okay. In another way of calling them, if you want to be fancy mathematically, you call this a Riemannian manifold. But a Riemannian manifold is nothing different than the surface, that we live. And I'm talking about relativity because whether the universe is flat or curved is going to determine a lot of things about our future. Scientists haven't really concluded about that. Okay, and you might have heard that gravity curves the space. The same thing. That's what it is. So, you see over here examples like what you see on the right-hand side is what the people call the Swiss roll, where if you want to travel on that, it's kind of like equivalent. You don't draw straight lines. You follow the geodesic, and you can unwrap it, and it can look like a straight line. This is called manifold learning. This is another example, where you have a teapot, where you shoot it from different angles. In reality, you don't really have a, you don't really need if all you're changing is the angle of the shot, everything lines on a circle. All you need, you don't really need these hundreds of thousands of dimensions of this pixel dimensions of this image. All you need is on which part of the circle you are. You just need one number. This is something else, the manifold of faces, where you have a face where it looks like left to right or top to bottom. Again, all these pictures are basically, if you're just looking at all these pictures, they are lying on a manifold that you basically have two dimensions. You have the X dimension and the Y dimension. Maybe I should talk about that. And here, what it's from a paper. So if you think about all the natural images, okay, that you can never see, the images that they make sense, because if I give you an array of pixels, okay, 1,000 by 1,000, that each pixel can be from 0 to 255. Not all, this is a huge number. It's 2 to the 1 million possible combinations, at least, something like that of that order. This is several, like, it's an insane number, much, much bigger than the size of our universe, all the atoms of our universe, okay, all the quarks of our universe, even bigger than that. So what you know is out of this 2 to the 1 million, actually 2 to the 25 million, now that I think better, 2 to the 255 million combinations. very few of them, a much smaller size, constitutes, you know, real images, images that you can see, like if you just walk on Earth, you can see around you. Okay, so this is an interesting problem. As you see over here, this is from a paper that they are trying to place a furniture. You know, you have an image of a couch and you're trying to place it in an image of a room. And as you can see, in the first image, the couch seems like flying. So the couch is not, like that image is not on the manifold of natural images, okay? Because couches don't fly. It lies on the manifold of all possible images. And basically, you know, what you're trying to do is you try to move it slowly until you hit the manifold of natural images. And now you see the final picture of the couch sits where it needs to sit. So what I'm trying to say over here is that although each image is represented by 1,000,000 pixels, in reality, it can be represented by a smaller vector, okay? Because, you know, it lies on a manifold of a smaller dimension. You know, as I said, all the 2 to the 255 billion combinations are not possible. Brianna, do we have until 12:45? What tell us how we're doing?
I think you can go ahead, and anyone who want to submit their questions or raise a hand, we can definitely make them ask the question even verbally. They can go ahead. I will ping you if we have any questions in between. Rishi, do you have any questions? I believe
Okay,
you're
well,
mute.
you feel free to interrupt if you need. Okay. So Bengio had a Eureka moment, and this is, you know, we're reaching towards the story of the 2,500 years. You know, the title was, it's an old idea. Like so far, we've been very geometric, and we're closely going towards deep learning. So we're getting into our story, you know, our days nowadays, where you know, Bengio is having this Eureka moment, and he's basically marrying embeddings with deep learning. He realizes that deep learning is what he needs. So the first wave of manifold learning methods or embedding methods were something that we call non-parametric. So basically, you give me all the data, and when I have all the data, I figure out, you know, I have the relationships, and I do this magic, mathematical magic, and I map them into this, you know, 2 dimensions, 10 dimensions, 100 dimensions. Like, you know, before where I showed you the map of United States where we did this. This is also a manifold learning method because I gave you some relations, and you were able to plot them on a 2-dimensional map. You know, you needed to have all the points. If I bring you some new points, some new cities, I would probably have to do the work from scratch. It won't be able to generalize, okay? So he said, well, you know, I need to create a method that it's parametric, which means that I need to learn this mapping. You give me these relations and I have to place you in coordinates. I need to use a model that is parametric so I can generalize in new data. Then the other thing that he thought about was, you know, instead of learning one task, okay, one relation at a time, and one concept at a time, it should be, let's try to learn, you know, more concepts at a time, more relations. So if we're trying to learn, you know, if you have an image, for example, you know, you can do segmentation. You can do object detection. You can do object labeling. You can do, you know, color replacement. Or, you know, if you think about image processing, which is a great example for deep learning, there's a lot of things you can do on them. Well, the more you do at the same time, so the more concepts you're looking at the image. You know, I'm trying to find people, animals, cars, airplanes. I'm trying to segment them. I'm trying to find the location where they are in the image. I'm trying to classify, you know, what do I have in the image, where do I have it, and extract it from the image. You know, trying to do all these things at the same time, okay, helps you learn these embeddings like this mapping really, really well and generalize very well. Okay, and the last thing which makes them distributed was, you know, as you know, in deep learning, you have recursive structure. You have structures that they are deep. You have several layers. So basically, each layer, you know, produces a different vector. Like the output of every layer is a different vector. It's a different embedding. Okay, embedding and vector is the same thing. So which means that now the representation is distributed. You know, for the same object, from the same image, I have lots of vectors, and each vector corresponds to different layer of the network, and it gives me different type of information. Okay, so that's the Eureka moment. Here I have a link to a podcast which is probably old now with the standards of deep learning. It's about 5 years old. It's called "Why Deep Learning is Like Building with Legos." It's from Nando De Freitas, a very prestigious researcher from DeepMind, and he was an Oxford professor as well. So you know, it's really interesting, and deep learning is kind of like building with Legos. Okay, this is why they have democratizing artificial intelligence. This is why anyone without a serious mathematical background can now become a deep learning expert. I've seen even ballet dancers getting hired by Google for doing the residency, working in deep learning, which means that, you know, you can learn it, you know, you can learn deep learning no matter where you're coming from. And the reason why you can do that, the reason why are Legos, think about why are Legos easy to build, is because you can take different pieces and the connector is always the same. Okay, you can take different sizes, different, you know, little humans, blah, 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 pieces. You can always connect them like that. The reason why you can do that is because, you know, let's say your data is like text. You use something called a transformer, and it makes it a vector. Vector again is an embedding. You have an image, you use a convolutional network, you get an embedding. You have click data, you use an MLP, you create an embedding. You have rules, you make an embedding. And what do you do with these embeddings? You know, you can do something really amazing. So you can have an image, you pass it through a convolutional neural network, it gives you a vector, you take that vector, you feed it into a different network called RNN, it gives you text. But you can go the other way around. You can take text, pass it through an RNN, which gives you a vector, an embedding in the end. You take this vector, you put it on it's not a CNN, it's called DCN, deconvolutional neural network, and it gives you an image. As a result, I can give you images and you can provide caption. But even the opposite, I can give you the caption and you can provide me an image. Okay, so and that was a toy problem. And this was, you know, and you can use it to do recommendations and search. You know, this is what YouTube could use, or any other retailer can use to have recommendations and search. Sorry. And here's like a data science exercise. I don't know how we're doing in terms of time.
We have about 10 minutes more. Rishi, would you go ahead with the questions, or Nick, would you want to continue?
Either way, Nick, I'm just fascinated with the things that you're talking about. Literally, I mean, I've not gotten this close to math in a long time, so it's real cool. You know, can you talk a little bit more around transfer learning?
About transfer learning?
Yeah. you build some, like you solve a problem using deep learning. How does it essentially, how would you apply transfer learning? So things that I've learned, ontology or something about, say, healthcare, how would I go about applying that into, say, detail? I'm answering a series of questions in healthcare. I understand healthcare ontology, what it means here. Is there, when we talk about transfer learning, what are the limitations there? What are the opportunities there? Can I take something that I've learned in healthcare, apply that to insurance or healthcare insurance? Probably yes, as a payer.
So,
Yeah.
It turns out that they have taken, networks. This really has to do with the size of the network and the, the size of the network and the number of training data. They've trained networks to play Go, the game of Go, and then they were able to take parts of the pre-trained network and reuse them and have the network play chess. They've done things where they train them on medical images and they can use them. So it turns out that deep learning, if you feed it enough data and if it's quite deep, you can make it be, quite, generalized really well. So I have another presentation. It's not here, but we can talk more about more about transfer learning. Like all these GPT-3 and GPT-X series is a great case of showing transfer learning and basically generalizability. Yeah, and it is very, very likely that you can train it on as you said, health insurance and then apply it into car insurance, although these are some they look very different domains.
Yeah.
Okay. So I'm just gonna wanna be practical and do the last example. So I want to talk about the importance of embedding for categorical data, which is an exercise that any data scientist has used before. So let's go back to one of the very basic things, which is one-hot encoding. So if somebody gives you, if one of your attributes is is using color, okay, then you use one-hot encoding. Okay, so for the black color, if you have 4 colors over here, you need 4 dimensions. The first is black, the second is the brown, the third is yellow and red. So this is a vector that only one element is non-zero, and it's 1. So we consider this a local representation, okay, because all the information is localized in one element of your vector, okay? And this has a lot of problems. If I have an extra color right now, I need to make, if I go and I add green, I need to retrain my model and have 5 dimensions. So in a simple regression example, you will just create a coefficient, 1 for black, 1 for brown, 1 for yellow, 1 for red. And let's say you're trying to compute the demand of a product, and you also put the price, okay, and one coefficient for the price. Now, a different approach would be to, to create a vector W for every color, okay, and use the dot product with the input, okay, and basically, instead of having one vector instead of having one hot encoding, like instead of having the 0, 1, 0, 0, 0, 0, 1, and so on, now you're going to have a W. You're going to have a W a W vector. Like you have to learn this, like as you're training your model, you're also learning a representation for its color. So, you know, if you're doing one-hot encoding, basically what you're doing is you're placing the colors on a simplex. This is called it's not exactly a simplex right now, but we can think about it as a simplex. But you're placing on the edges of a shape that, and all of them are equidistant, you know, almost. Actually, this and this is not equidistant. So I have 4 colors. I would need a 4-dimensional simplex. It's not easy to visualize, but you can think about if you had 3, you're placing them on a pyramid so that all of them, you know, are having the same distance. Okay. Now, when you're doing the embedding, when you're doing the other representation where you're actually learning the representation vector of the color, you would get something different, because let's say if dark colors are selling better than light colors, it will take the dark colors and put them closer, okay, and the lighter will put them closer. So what I'm trying to say is that by using the embedding approach, as you're training your supervised model, or even your unsupervised, it doesn't really matter, you're learning something about your discrete variables. Again, one-hot encoding, all colors have the same distance from each other. You choose to use the embedding, the colors, you know, are placed based on their semantic similarity. And, you know, I don't think, you know, this is probably a little bit more advanced, but there's something even more fancy than that. It's called graph neural networks. And I'll just talk a little bit about generative models, and then I'll stop. These are the famous GANs. So I can give you a vector, and then I have something that's called a generative deep learning network. And I can give a random vector, not any vector, and it can generate you image, text, music, video, whatever you want. And in some cases, I can say, well, I give you a vector, and the first element will control the place where the image is looking. Sorry, yeah, the direction, the azimuth, and the elevation. So I can tell you, generate me images that are looking, you know, left, north, or south, east, or whatever you want. And I can give you, you know, this is like an example where no, it's probably not. Let's skip this one. Let's move to Euclidean geometry. You know, that example was a little bit complicated. I shouldn't have presented it. So far, that's going to be my last part. Euclidean space, it's a place that we live in our every life. It is a very boring place to live in. Okay. Euclidean space is flat and means that the space has no information. There's no information stored in space. So whether you're here and you go a few meters away, nothing has changed. I do have a YouTube video which is fascinating, which is talk about non-Euclidean universe, and we should, you know, you should really watch it. It's really fun. It's from the 70s, and it's amazing, you know, what these guys did with 70s, did with very few computer graphics. So, you know, it's really fascinating to see how a word that does not obey to the Euclidean plane geometry behaves. And basically, if there is something that you need to keep in your mind, you know, Euclidean and non-Euclidean geometries are coming very aggressively in deep learning. We're going to see them more and more. Is that they can basically fit a lot of information in limited space. Okay, so for example, if you know you have 4 points that they all have to be 1 unit away, you know, the distance between them, like the distance, you know, this is a classic example. The distance from here to here is 1, from here to here is 1, okay, and the distance from here to here has to be 2, okay, because it's 1 plus 1 is 2, okay. But if you plot them on a 2-dimensional space, you introduce a distortion, because now the distance is square root of 2, okay. And the same thing over here. Here you introduced even, you know, you introduced different type of distortion. So there is a problem. The Euclidean distance cannot really represent this graph accurately. You need to go to high dimensions, and this is a problem because you know, the more distortion, the more dimensions you need, the more space you need for your computation. In some cases, it's fairly impossible. And this is kind of like an example that when you're taking things that they live on a sphere and you put them in 2 dimensions, you introduce so much distortion. What this plot is trying to show you over here, all of us have seen Greenland and we think that it's a huge continent. Guess what? It's not really huge. It's the size of Mexico. Okay. But when you place it, things that are close to the poles appear to be much higher. So this is how Mexico would look like if it was up there. Okay. And this is how, if you take United States and you place them closer to the North Pole, it's going to be look, you know, bigger than Europe. Okay. And the same if you take Australia, is as big as, I think, would look as big as China, you know, if you place it closer to the pole. So I'm not going to continue with that. All I'm trying to say over here is that if you place, you know, the hierarchy of mammals on a hyperbolic geometry, you can get stunning results. You can get something that it's really great, closer to reality. And if you look at the metrics in classification and other problems, it's orders of magnitude higher than Euclidean. You know, basically it says you that what you can do, like look at the error. The error is 4.9 versus 3,500. It's, I won't go to the details what error is this. Is that you use 5 dimensions in the hyperbolic geometry, okay? And even if you use 200 dimensions in Euclidean, you can't even get close. Like the best you can get with this one is 91 versus 5, okay? Several other cases. So what you can do with 5 dimensions in hyperbolic geometry, you can't even do it with 200. And same here. So, oh, okay, we managed to compute. Embeddings is the new normalization of data. Embedding summarizes any info in a fixed vector. Complicated processing can be done with dot products. Different types of data can pass information to each other, and embedding is the basic ingredient of deep learning. Okay, so thank you so much. I just finished right on time. And
NIKOLAOS, this was outstanding. You're right. You went through a lot of stuff very fast, and this is easily a 2-hour-long presentation, and now you skipped through a bunch of things. I would have loved to stop you a couple other places, but I still wanted you to get through the deck. This is fascinating.
Okay, we'll share the deck with you.
Yeah.
And I don't know if there are not any questions. Unfortunately, I realized this.
Yeah, I'm sure you have
there's more applications. Thank you very much, everyone.